Yeah, I already pressed.
All right, folks, welcome to the 66th linear algebra lecture. Today we're going to go back to one of the fundamental topics in linear algebra, one that we also covered yesterday, and that is the topic of dot products. Okay, so first and foremost, today's do now is going to try to review the concept of dot products, and then we're going to go ahead to the lesson where I'm going to try to introduce the idea of dot products from a different perspective, and then finally I'm going to show you the different inequalities regarding the dot product, why the dot product is useful, etc., etc. But today the main highlight is a different perspective of the dot product. Okay, so let's go ahead and first and foremost begin with the do now. Okay, so today's do now is quite simple. So let's take a look at what it is. Okay, so today's do now, I will be, of course, inviting our students as normal. And here's the do now, okay? Find the dot product of the following two vectors. Okay, I'll be using 2D vectors, but remember that the dot product is applicable to n dimensions, okay? I just want to keep things simple, keep our brain sharp. So let's see, let's try to think of some compatible numbers, perhaps 1, 3, and can I get a number from the audience? 2, 4. Can we handle that? Can you give me a negative y component?
2, -1.
2, -1. Okay, sounds great. So if I'll give the audience a few seconds to go ahead and try this do now, and while you're trying, we're gonna go ahead and take a look at the solution. So please take a few seconds to go ahead, try the do now, and then after you tried it, we're gonna go ahead and provide the solution to the audience. Okay, so let's just wait for the audience to get ready with a solution. Okay. Okay, great. Of course, hopefully some of you in the audience realize that linear algebra and algebra are not the same. They're a tad bit different. Okay, so I think our audience is ready for the answer. Would anyone from the live audience like to try this problem? Oh, I have one invitee. Oh, he wants to try this problem. Oh, okay. Here you go. Okay, so the invitee has accepted the request, and he asked me to write out his solution. So he said we have to multiply the corresponding components of each vector. So what does he mean by that? Well, he means take the first components of both vectors, 1 times 2. We're going to multiply them. Okay, and we're going to add it to the product of the second components, plus 3 times -1. Okay, and this is going to be what? Well, would the live audience like to tell me what this is?
2 -3.
2 minus 3. So 2 minus 3 is just simply going to be -1, right? So hopefully that served as a review for you. Hopefully that's not anything new. If it is, you can go ahead and look at our past few lectures. Now we're going to move on to the lesson where we're going to take a different perspective of the dot product, okay? And our new perspective begins with something very unusual, and that is the printer paper, folks. Now, please raise your hand in the audience if you have some HP printer paper, okay? Because you're going to need that for this demonstration. Okay, so does everyone in the audience see our demonstration? We have a printer paper, but more importantly than a printer paper, we have the coordinate plane, folks, okay? Now, we're going to actually try out this dot product on this analog, Okay, there's a pin back there, and okay, I'm almost bled to death. But this is an analog coordinate plane, and we're gonna try out to find the dot product of these two vectors using these two coordinate planes. Okay, so let's go ahead and find the dot product of these two vectors using our 3D coordinate Cartesian plane. So how am I gonna do that? First and foremost, you have to understand the components of this coordinate plane, right? As usual, we are in the Cartesian coordinate system. So we have an x-axis, I will label that with an x, and we have a y-axis, which I will label with a y. No surprise there, I hope. Now what we're gonna do is place our vectors. So regrettably, I will have to hold this the rest of the life, but this is no problem, okay? Now, what we're gonna do is first graph our first vector. Audience, what is our first vector?
1, 3.
Okay, 1, 3. Now, to graph our first vector, what we need is something unexpected. Algebra 1, folks. Or, really, what we need are pins, you see? So I'm gonna grab a pin and attach it to my coordinate plane. So let's navigate to 1, 3. 1, 3. Boom, there goes my pin. Hopefully everyone can see my red pin.
Yes.
Okay, next, what is my next vector?
2, -1.
2, -1. Let's navigate to 2, -1, which I will represent with this purple dot. Okay, so 2, -1 is going to be 2, -1. Boom, seems like I almost predicted that. Huh. Kind of scary. Now, I have two vectors, but I need a way to visualize them, okay? So I've got some handy dandy. So let's see if this can actually work. So let's first attach them, and I'll show them to the live audience. So.
I know what you want to do. So,
Oh wow!
no, I'll give you this.
Holy
The
shit.
tension is not enough to hold it. So I got a small one. See?
Oh yes. Okay. So we actually blew one pin out of the water, so the audience will have to be careful of that.
You're lucky.
Yeah. Oh, thank you. Okay. So good. We don't need any more, right?
No.
So let's go ahead and attach these pins. Let's see what our vectors end up looking like. Okay. Now this demonstration can go horribly wrong, folks. So don't try this at home. Okay. So how do our two vectors look like? Let's take a look. If I can get them to look right in the first place, that right there would be an achievement. Okay. Now while I'm doing this, I want you to keep in mind that these physical demonstrations are extremely dangerous. Okay. I'm only doing this because I'm great at linear algebra. So try to keep that in mind when you're deciding whether to do this for yourself. Okay, so I have visualized one of my vectors, right? One of my vectors, which is 1, 3. Now I'm going to try to visualize my other vector with yet another, what do we call it? A ribbon. Or you can call it a, forget it. Okay, we're just going to grab these suckers, okay? That seems to be an easier thing to do. Okay, so let's grab them. Because pinning them down is too hard to do. So our first vector, 1, 3. Here it is, right? And our second vector, 2, -1. There it is. Now, what do we do when we when we evaluate the dot product? Do we get a vector or a scalar?
Scatter.
A scalar, and we get -1, right?
Yes.
But what does that mean? What does that mean? Another way of phrasing the dot product is how similar are two vectors, okay? How similar are two vectors. Okay? This question is the same thing as what is the dot product of these two vectors. Okay? Let me show you what I mean. Okay, so here we evaluated the dot product of 1, 3. So let's write, I'll call this vector u, and I'll call this vector v. Okay? So here goes u, here goes v. So when I evaluated their dot product, what did I get? What scalar did I get? What scalar did I get? Huh?
-1.
-1. So does that mean they're very alike? or they're very similar, or they're very different?
Direction doesn't matter.
Oh, but it does. The negative tells me that these two vectors are going in opposite directions, right?
Yeah.
You can see that they're going in opposite directions. So another way to phrase the dot product is to phrase it as a projection. Okay, so let me show you what I mean. Okay, so we have these two vectors. Now I'm going to project u onto v.
What does projection mean? Explain.
Okay, great question, great question. So let's go ahead and explain what we mean by projection. So let me actually draw the coordinate plane here on the board. So here we are. Let's say I have two vectors. You give me u, and let's say I have another vector v. So my goal is to project. Here's my goal. Project u onto v. What do I mean by that? What I mean is that if I have a kind of line through the origin passing through v, I want to project u onto this line. So let me visually show you what I mean. Okay, so this will be a perpendicular line.
Say it again.
Oh, okay. So my goal is to project my vector u onto the vector v. How can I do that? What I have to do is draw a perpendicular line and then find the horizontal component of this vector going in the direction of v. So here it is. Okay, so this is gonna be what? What is this gonna be? U dot v with the magnitude of v. Let's try to understand what I just did. Okay, what did I start with? I had two vectors, right?
Yes.
I had two vectors u and v. I wanted to project my vector u onto vector v. What does that even mean? Let me try to give you another perspective. Let's say you are standing on the sidewalk and the sun is shining on you. So sun is shining on you and the sun shine on you and project a shadow on the ground. Okay, so you can kind of think I am a vector and my shadow is another vector. Okay, my shadow is a projection of my image on the ground. Just like that, you can kind of imagine that we have a sun over here. This vector u is a sun, and it's kind of emitting light in all directions. And in emitting the light, it gives a shadow. It gives a shadow of its original image. Okay, and that's the projection. So I'm gonna make this much easier. I'm gonna try to make this idea much easier to grasp by thinking of the basis vectors. Okay, so right now we have been thinking of some audience given vectors, but now I'm gonna try to simplify this idea with the basis vectors. Okay, this is as simple as we can get, right? The x and y plane. Okay, my goal is to understand the meaning of the dot product. That's my goal. What does this even mean? I know it gives me a scalar, but what does that scalar mean? Okay, so let's say I have two vectors. Okay, so I have one vector, I'll call that u. Okay, and I'll have another vector. Let's say I call that v. Okay, this is what the projection of u onto v will look like. Okay, so that's a projection.
Why is smaller?
Oh, that's a good question. So it can be smaller, same size, or bigger, depending on the other vector, the vector that I'm projecting onto. Okay, so you can kind of imagine this as the sun, and you can imagine this on the ground, right? This is the ground. The shadow is going to be on the ground. If the ground is tilted, the shadow can be longer than you or shorter than you, right? So this, you can kind of, the projection is like a shadow. I'll call it proj for projection. Okay, so here is how we can understand that idea. I'm going to reduce it to the basis vectors. Okay, is gonna become a very simple idea, and you will see that this complicated thing is now actually very simple. Okay, ready? Here it is. Here is one vector. Okay, here is one vector, and here is my basis vector. What is this basis vector called? In the x direction, what is the basis vector?
B.
I hat is the basis vector in the x direction, right? Now I have this vector, let's call it u, right? Okay, everyone knows where the sun is, right? Okay, audience. So we have the sun shining here. The sun is shining, and the sun is casting a shadow. The sun looks at the vector and it casts a shadow on the ground. This is how the shadow of our vector looks like. So audience, can you tell me how big this shadow is gonna be? Well, it's quite simple, right? It's gonna be the magnitude of our vector times cosine of the angle between the ground and my vector.
Say it again.
Oh, okay, yeah. So let's say I have the vector u, right? The sun is shining on my vector. So when the sun shines, it makes a shadow, right? So here is the shadow of my vector, okay? And the size of my shadow is gonna be the size of my vector times the angle between my vector and the ground, okay? So don't worry, we're gonna get a lot of practice with this idea, but the crucial idea is that the dot product is essentially a projection. It helps you understand how similar two vectors are. Okay, so that's basically the lesson, and that was the exercise. So thank you for watching. Yeah.